are knotted to each other. So it's a big mess. And what you want to do is you want to pull that one spaghetti and pull out all of them which are connected, and the rest is left in there. It only works if you put a bit of oil in there, otherwise you get oil. So it must be a bit screw-proof. So you pull at this string, and then you get these three, and the rest remains in there. That's basically what this algorithm does. The key point is that you find the spaghettis which are reachable from the outside. And that's what we call the roots. The roots are the spaghetti which are seen on the outside. And then you pull on the roots and put all those objects into an extra pot. And then everything in the pot is garbage, which is left in there. That's what it does. So after it has copied over all reachable objects to this point, the rest is garbage. And we can either continue here and say, okay, this is now our allocation point, and we continue to the end. Or there's a variant which is used here and which is used in others, but this is the basic idea. There's a variant because sometimes the set of copied objects is smaller, so you have a bigger called Eden and a smaller survival space. But generally the idea is the same. You have two pots and copy from one to the other. Now, after a few copies, you would say, I'm bored of copying, maybe this is too much work to copy it back and forth. So what it does, it keeps account of how often an object has been copied. And after this count has expired, the count is dynamic, by the way, so it depends on how full this is after a copy, after a so-called scavenge. This is a scavenge operation. It depends on how full the semi-spaces are on the scavenge. If it's very full, then it says I should probably tenure, make them old earlier. And if it's relatively empty, it leaves them longer here for playing. So after a while, when it's bored of copying, it says the next time I don't copy into the semi-space, but I copy into the old space. And the old space is another area which is much, much bigger. 100 megabyte or even half a gigabyte. And then here the same happens more or less. So I have an allocation point, and to copy it there, it copies it at the allocation point. Now this one is very, very big, and the question is how do we connect here? I will show this in a minute, but the next thing is how do we find, I talked about the roots here, how do we find references from here to there? Because we should not forget that it's not only the globals, it's also the old objects which already point through this space which have to be considered to copy over. And for this, the system keeps the so-called remembered set. A remembered set points to all objects which are known to have references to new space objects. And when I do this scavenge operation, I have to look at the remembered set also. That means I have to look at all these objects if they still have references to that. If no longer, they are removed from the remembered set. But if they have to be considered true for copying. So they are considered also roots. And how do I keep the remembered set up to date? Well, the remembered set must be kept up to date, or can be kept up to date very simple. Whenever I store a reference to another object in an object, which means I have one object, O1, and I have another object, O2, and I create a pointer from here to there, I have to look if I point into a newer age. Actually, this is not just 2 generations, it's more. But whenever I create a pointer from an old age to a new age, this one must go into the remembered set. And then there's an additional bit in the header which says it is already in the remembered set, which means when I write multiple times to the same object, I don't do this all over again. It's only once in the remembered set. This algorithm was also, this is a name which we should write down because he's really a clever guy. It was also invented by Mr. Unger.
I think it's with an A.
Huh?
I think it's with an A instead of an E.
You mean
with an A. I think it is with an A. You
is an A or
A?
Yeah.
Could be, I'd be, okay. Anyway, he invented that for Well, in the 80s, early 80s, there was quite a lot of stuff going on. And they even built a hardware for Smalltalk, so it's a pity that it's no longer done today. Now, there's another thing talking about these things. This garbage collector has a few, well, this one has to also be cleared, because it might also run through after a time. So here is a background mark and sweep, which is incrementally. The mark and sweep algorithm is just following recursively the pointers, marking them, and in a second phase, it looks for unmarked objects and put them on a free list. So here is an additional free list. Actually, it's many free lists. There's about 1,000 free lists for different sizes, so that I don't have to search when I search for a particular size. And this free list links all the free objects of the same size together. So when I have to tenure an object down there, I first do it in the free list, and then I advance the pointer. And this is done, and the mark and sweep is done in the background. So whenever it finds time to do nothing, actually it's driven by a process. It marks a few objects and then it continues, and in the end collects, it sweeps a few objects and continues. So it's an incremental process. The system never stops. Now we can make a few quantitative statements about what is the maximum pause time, for example. What is the worst case for this garbage collector? Or what is the best case? Funny enough, the best case is if you have garbage. If you just allocate garbage and it's not needed anymore, then nothing has to be copied. And it's immediately done. So for full garbage, if you only create point new, the garbage collect time is almost zero. It's just the time to scan a few tokens and stuff, but it's almost zero. So whenever somebody tells you to produce, we have to avoid garbage, rubbish, it's not true. It's true for some garbage collectors, for a market sweep, it's true, but not for the generation scan machine scheme which we use here. And the worst case is obviously when every object survives, which means when this one is full, and then everything has to be copied over. And we can actually give an upper bound on the time which is when there, which is almost memory copying speed. There's a little bit overhead to this. So by setting the size of this area, you can adjust the maximum time. Actually, we had a real-time system running for factory automation where we guarantee that it's never blocking longer than 50 milliseconds. That was a long time ago, and at that time we limited it to 100 kilobytes. Nowadays machines are much faster, but with 400 kilobytes you would probably be in the 5 to 8 millisecond range, depending on memory speed and cache size and all that stuff. So I think this is a quite interesting thing to remember when people say you should, for example, have an object pool. What is an object pool doing if you want to avoid garbage? An object pool means you have a class variable where you keep objects around to avoid allocating them again. The object pool will do counterintuitive, will do exactly the opposite of what you want. The object pool leads to objects go into the old space. And as you now know, the old space is much harder to reclaim than the new space. So if you know that an object is not used, don't use an object pool because garbage is cheap. And this scheme is used in Visual Works, in Squeak, in Smalltalk X, I think in all modern Smalltalks. Maybe, I'm not sure about Dolphin, but I don't even think Dolphin would use another garbage collector. It has been a problem with the early Java engines. They used very stupid and naive garbage collectors. But nowadays, things have completely changed. Also in the Java world, they have modern garbage collectors and they have the same things. Good.